In this video, we're going to discuss how to deal with integrals which involve these forms, the square roots of a squared minus u squared, a squared plus u squared, and u squared minus a squared. Here, u is a variable and a is a positive constant. I can tell you the breakdown right now. If we encounter the form a squared minus u squared under a square root, then we let u equals a sine theta. If we encounter a squared plus u squared under square root, then we let u equal a tangent theta. And for this third form, we let u equal a secant theta. Now, to explain why these substitutions work, I'm going to first make a short digression. I want to warn you that the square root of the square of a number is not equal to the original number all the time. For example, the square root of -1 squared is not equal to -1. However, the square root of x squared is equal to the absolute value of x, right? I mean, for example, we see right here, if we plug in -1 and square that, then take its square root, we get 1, but that's equal to the absolute value of -1. Now, let's suppose that we start with a positive constant a, and we encounter an integral involving the square root of a squared minus u squared. Let's see what happens if we do make the substitution that I recommended on the previous slide. Well, replacing u with a sine theta, we get this. And then we can factor out an a squared from both terms under the square root. And then we can apply the Pythagorean identity. 1 minus sine squared theta is equal to cosine squared theta. Okay, but then we can break that up into the square root of a squared and the square root of cosine squared, giving us absolute value of a times absolute value of cosine theta. But a is positive, so absolute value of a is equal to a. Now the goal is to try to get rid of those absolute value signs somehow. In other words, we'd like to ensure that cosine theta is positive. Well, let's see how we can do this. If the square root of a squared minus u squared is well defined, then that tells us that u lies between -a and a. And therefore it's possible to find value of theta between -pi/2 and pi/2 such that u equals a sine theta. Graphically, this is easy to see because if u is any number between -a and a along this y-axis here, then we can find some point on the curve a sine theta which has u as a y-coordinate, and then that corresponding x-coordinate gives us a theta. Then with this restriction on theta, we're certain that cosine will be non-negative. Cosine of any angle in this range is non-negative, and therefore we do get this nice simplification that we were looking for. The absolute values go away so long as we restrict theta to this range. Okay, so let's see how this goes in practice. We encounter an a squared minus u squared here, where u is equal to x and a is equal to 3. So let's let x equals 3 sine theta, and in the back of our mind we'll remember that theta lies between -pi/2 and pi/2. Then we know that the square root of 9 minus x squared is equal to 3 cosine theta. We've already discussed that. And we can compute the differential of x just by computing the differential of both sides of this equation. dx is equal to, take the derivative, 3 cosine theta times d theta. And now we just rewrite the original integral involving, or in terms of theta instead of x. dx is written explicitly here, x is written explicitly here, and we've already computed this expression under the square root. It's there. Okay, so now let's simplify. I see 3 cosine theta will cancel with 3 cosine theta here. And then on the bottom we have a 9 because that's 3 squared. And we also have a sine squared on bottom. So in other words, that's cosecant squared theta. And then there's a 1/9 out front. Okay, well that's good news because cosecant squared theta is an integral which we know. It's negative cotangent theta. Okay, so then how do we back substitute? How can I rewrite this in terms of x again? Well, I'm going to have to solve for cotangent theta somehow. And the way I recommend doing this is by using geometry. We know that x equals 3 sine theta, and so we can form this triangle here. If theta is this angle here, then to say that x equals 3 sine theta is the same as to say sine theta equals x over 3. But remember, sine is opposite over hypotenuse. So opposite over hypotenuse is supposed to be x over 3. Then, if we use the Pythagorean theorem, this squared plus this squared should be equal to this squared, and therefore we conclude that this side is equal to square root of 9 minus x squared. Okay, well now that we've finished this triangle, we can simply write down what cotangent theta is. It's, let's see, tangent theta is opposite over adjacent, so cotangent is adjacent over opposite. And so that's how I get this fraction here. Well, this is good because now we can back substitute like we needed to, and here's our final answer for this integral. Now it's natural to ask, can we similarly restrict theta so that making a substitution u equals a tangent theta will make this square root of a squared plus u squared into some simple expression with no absolute values? Well, again, the answer is yes. Let's take a look at what this expression simplifies to. As before, we can replace u squared with a tangent, or a squared tangent squared theta, pull out that a squared from both terms, then use a Pythagorean identity, 1 plus tangent squared equals secant squared, and then split those up, and we know that the square root of a squared is absolute value of a, and the square root of secant squared is absolute value of secant, and a is positive, so a is equal to its own absolute value. So we're looking for a range of theta where secant is positive. Well, take a look at this graph here. This is one of the many curves that appear in the graph of tangent. Remember, this was in a periodic function. This curve is just repeated over and over and over again. So we notice that if u is any number at all lying on the y-axis, then we can draw some horizontal line over to the curve, and we find that over that lies some angle theta between negative pi over 2 and pi over 2. This tells us that we can find some theta lying in this range such that u equals tangent theta, or a tangent theta. Okay, then with this restriction on theta, we know that secant theta is positive. Again, this is this range of theta represents the right half of the unit circle, and so cosine is positive there, and hence so is secant. And so we see this simplification gets rid of the absolute value signs as we want. Okay, let's see how this works in practice. We see the form square root of a squared plus u squared. Here u is equal to 2x and a is equal to the square root of 3. Then we let 2x equals square root of 3 tangent theta, and in the back of our heads we're keeping in mind that theta lies in this range. Then this expression under the square root simplifies to just square root of 3 secant theta, as we proved on the previous slide. And to get the differential dx, we need to take this this equation where we made our substitution and take the differential of both sides. For the left side, it's 2dx, and for the right side, it's square root of 3 secant squared theta d theta. And now we're ready to rewrite our integral. Okay, now we're ready to simplify this. How is it going to simplify? Well, I see on the bottom we have secant cubed. That will cancel with 2 of the secants on top. So we'll now have 1 secant on the bottom, which is the same as having just cosine on top. Also, I notice that there are 3 square roots of 3 on the bottom. One of those will cancel with this one up top, and I'll be left with 2 lots of the square root of 3, which will multiply up to just 3. And then we have this 2 down here, so the bottom will have 6. So all that means we have 1 over 6 times integral of cosine theta d theta. And now we're ready to take that antiderivative. It's just sine. And now we need to back substitute, and we do this again by taking a look at this triangle. If we write 2x equals square root of 3 tangent theta, that's the same as saying tangent theta is 2x over square root 3. On the other hand, tangent theta is opposite over adjacent. So 2x over square root 3, and then this hypotenuse is determined again by the Pythagorean theorem. This squared plus this squared is supposed to equal this squared, and so this side must end up being square root of 4x squared plus 3. Okay, well then we can just look at this and say sine theta is opposite over hypotenuse. Now that's 2x over that square root expression. And so now we can back substitute like we needed to, and here's our final answer for the integral. Alright, let's ask ourselves one more time. Can we similarly restrict theta so that the substitution u equals a secant theta makes this square root expression a simple expression with no absolute values? The answer is yes, but unfortunately theta is restricted to two separate intervals this time, rather than just the one. To see this, let's first see what it is that we need to be positive so that there's no absolute value. Well, let's substitute u equals a secant theta, factor out that a squared, apply the Pythagorean identity secant squared theta minus 1 equals tangent squared, and then that simplifies as it has in the past few cases. So we need some range of theta where tangent is always positive. Okay, well let's take a look at the graph of secant theta. Recall that this is made up of several of these sort of U-shaped curves alternating between being above the horizontal axis and below the horizontal axis. I've indicated that part of this curve should be in red. These are the intervals where I want to restrict my theta. You see, if u is any number bigger than a, or less than negative a, then there exists some horizontal line over to the curve in red. If u was down here, that horizontal line would have to go way over here, so that the corresponding theta would lie in this little interval here. Why am I bothering to choose these two intervals? The answer is tangent theta, remember, is supposed to be positive, and tangent theta is positive between 0 and pi over 2, and it's negative between pi over 2 and pi, so I don't want to use that interval, but it's positive again from pi to 3 pi over 2. So that's why I'm choosing these two intervals. And we can see here then that it is possible to find some theta in those two separate intervals such that u equals a secant theta. And with this restriction on theta, we see that tangent is positive, so that this simplifies like we wanted to. Okay, so to see how this works, let's look at this integral here, and this time it's a definite integral. So we're encountering u squared minus a squared, where u is just x and a is 2. So we let x equal 2 secant theta, and in the back of our heads we're remembering theta lies in one of these two ranges here. Then this square root expression we've already computed is equal to 2 tangent theta, and then we need to compute the differential just by computing differential of both sides of this. Okay, now we're ready to try to change the limits of integration. The first limit is x equals 2. Well, then what value of theta corresponds to x equals 2? Well, we're just going to plug in x equals 2 to our substitution equation. So x equals 2 secant theta becomes 2 equals 2 secant theta. Alright, and we're solving for theta, keeping in mind that theta lies in this range or in this range. So let's divide by 2, and then invert both sides. 1 over 1 is just 1. And so we see that we're looking for some value of theta in this range which has cosine equal to 1. Remember, cosine equals 1 is the rightmost point on the unit circle. And so that's the angle 0, or 2 pi. And looks like 0 is in my range, so theta equals 0. Okay, let's try the top limit of integration. If x equals 2 square root of 2, then we substitute that into this substitution equation. So 2 square root of 2 equals 2 secant theta. Divide both sides by 2, invert both sides so that we can get a cosine, and remember that 1 over square root of 2 is equal to square root of 2 over 2, which might be more familiar, right? That's the cosine of pi over 4, which does lie in this range again. So we conclude that theta is pi over 4. Okay, now we're ready to rewrite our integral. The square root expression we already found was 2 tan theta. Dx we found was this, and then x was our original substitution, so that goes right there. Moreover, we changed the limits of integration to 0 to pi over 4. Okay, now we're ready to simplify. I see that 2 secant theta cancels with 2 secant theta. This other 2 can come out front, and then there are 2 tangents remaining, so we have tangent squared theta d theta. To do this, we're going to use the Pythagorean identity, switching this to secant squared theta minus 1, as described in the previous video. And then these are two basic integrals. Now we plug in pi over 4, and then we plug in 0, and then we simplify. Okay, I want to look at this integral one more time. I want to compute this integral over a slightly different interval. Notice this time I'm going from negative 2 square root 2 up to negative 2. So everything's going to be about the same. We're still making the same substitution, but how are we going to change the limits? Well, we're going to use the same procedure as before. We're just going to substitute each individual limit of integration into the substitution equation, then solve for theta. Okay, divide by 2, invert both sides. But now cosine of theta is equal to negative 1 over square root 2 instead of positive. And remember that theta lies in the range from 0 to pi over 2, or from pi to 3 pi over 2. So in this case, that tells us that theta must lie in the range from pi to 3 pi over 2. Because cosine is negative, that means it's on the left side of the unit circle. Okay, that tells us that theta must be 5 pi over 4. Okay, now let's determine what the upper limit should be changed to. So same procedure, we're going to substitute that into this equation, then divide by 2, invert both sides. Remember that negative 1 over 1 is the same thing as negative 1. And then looking at this, I see that cosine theta is negative 1, which means that we're talking about the leftmost point on the unit circle, which is the angle pi, which is in the range of angles that I was restricting theta to. So this tells us that theta must be equal to pi. So this time we rewrite our integral, and well, all this stuff is the same, but now our limits are from 5 pi over 4 to pi, even though 5 pi over 4 is larger than pi. Okay, so again, our approach to the integral is the same. But this time we plug in pi first, and then we plug in 5 pi over 4. And this time when we simplify, we get the negative of the answer we got last time. To see that, let's see, we got negative 2 times 1 gives us a negative 2. And I also see that negative 2 times negative 5 pi over 4 is the same thing as positive 5 pi over 2. But then I also have minus 2 pi here. So 5 pi over 2 minus 2 pi is equal to pi over 2. Okay, let's recap. For integrals involving square root of a squared minus u squared, we let u equal a sine theta, and we keep in mind that theta is restricted to lie on the right half of the unit circle, possibly including pi over 2 and negative pi over 2. For integrals involving a squared plus u squared under square root, we let u equal a tangent theta, where this time theta lies in the right half of the unit circle, excluding negative pi over 2 and pi over 2. And for integrals involving the square root of u squared minus a squared, we let u equal a secant theta, where theta lies in quadrants 1 and 3 of the unit circle. And I've just noticed that this is a slight error. This should be strictly less than, not equal to, right here. Otherwise, this is all correct. Okay, in the next video we're going to talk about one more integration technique called partial fraction decomposition. But before we do, I'd like you to try to evaluate this integral. And just remember that you may need to refer back to how to compute trigonometric integrals from the previous video.